So let's continue on with our story of SVMs. Some questions were asked by you guys during the break, and I will try to answer some of them as we go along. So the next thing I want to talk about is that support vector machines can also be used for regression as opposed to just classification. And later on we'll talk about something called relevance vector machines, which are a more modern version of support vector machines. So they've been proposed for regression, which is quite popular in practice. So you replace the squared error function with an epsilon insensitive error function. So in SVR regression or support vector regression, the error function that is used is this error function. Y of x is the prediction, so it's W transpose xi plus b. And as we know now that, and we'll show again later on, that instead of using W transpose xi, we can also use k W xi, which is basically the kernel connection to them. That can also be done. So suppose that's the prediction. T is the label that you see, is a dependent variable. So you look at the error between your prediction and the variable, take at the absolute value of that error, subtract epsilon from that and take the positive part. Meaning that if the quantity inside is positive, take it to be that, and if the quantity inside is negative, you set it equal to 0. So in this particular case, if the error happens to be less than epsilon, you do not score that as an error. If the error happens to be greater than epsilon, then take that to be the error. So the picture is this. So if you look at the error, between minus epsilon to plus epsilon, you don't score the error at all. It's a dead zone. For those of you who have seen maybe some control engineering, sometimes they do this with dead zone. I'm okay if it comes within plus or minus epsilon, and if it is greater than epsilon, then you linearly increase the penalty. If it's less than epsilon, then you linearly increase the penalty. Okay, so this is analogous to, this is very analogous to, where did that go? This kind of a hinge loss function, except that here we are not talking, we don't have classification, we have regression, which means that I'm using a symmetric error on both directions. Okay, so L epsilon only penalizes predictions that are more than epsilon away from the target, result in sparse solutions where only a subset of the training points matter. So again, we want to basically have this idea that there is some robustness, that a few points will matter. Only in on the points that lie on that perimeter is going to matter. And then you run this. The regularized objective function for SVM regression is then given by this quantity. This is the error, and here I've just written out Yx in more gory detail. C is again, don't stand over there. So C is again chosen by cross validation, and this is the extra term which is trying to keep the W small. If you write it out, the primal SVR regression problem becomes this. There is that error over there. You introduce two slack variables, Ci and C hat I. One of them is for one side error, the other one is on the other side error. C and C hat has to be greater than or equal to 0. The slack variable C and C hat are non-zero only for prediction outside the epsilon insensitive tube. If you are within, then both of them are equal to 0. The primal problem is convex, so you can define a dual problem obtained by taking the Lagrangian dual of the two linear constraints. Now we have two linear constraints. You put them into the objective using a Lagrange multiplier, and then you can reset what is going to happen there. The kernel trick can also be used in the dual, and ultimately what you end up getting is that if you solve the dual, the regression function looks like some ai minus a hat I, where ai's and a hat i's are Lagrange multipliers, kxxi plus b. So here we have jumped already to use the kernel trick. Up until this point, I've been using inner products, and over here I'm saying that once you know the story for inner products, you can very easily tell what's going to happen for when you are using a kernel. Now in the homework that has been assigned for this module, you will actually figure out how to do this SVR, not by using duality, but by using this min-max trick that we talked about yesterday. Because it turns out that it's a nicer way to do the min-max trick, and you can get to the same answer. This is what the picture looks like. Now, if you look at this epsilon tube, everything that is in here has the c hat equal to 0. So over here c is greater than 0, over here c hat is greater than 0, in between both of them are equal to 0. The points above the tube have one of the slack variables positive and the other one 0. The points below the tube have the other slack variable, and the points inside the epsilon tube have both the slack variables 0. Only the points on the edge of the tube or outside the tube are support vectors. So right at the edge or outside, those are the ones that are going to be support vectors. Anything that is within here will not be a support vector. So the points that are, if your regression is good, then many of the points are not going to be defining the support vector because they will lie within this bound. Okay. Pretty much the same ideas that you can use for singular value, not singular value, for support vector machines for classification, you can use the same thing for regression. Now, what I want to do is show you a slightly, okay, let's do two things here. Okay, the detour that I'm going to take here is going to take us away a little bit, and at the end of the day, what I'm talking about here in the next few slides is going to be more mathematical, less practical, but it will give you an idea for what do these kernels do and why are kernels starting to become so important. So before we go there, how many of you have come across this word Hilbert space? Anybody? Hilbert spaces? No. Okay, so let me go in that direction a little bit, tell you a little bit more, and then we'll come back to this story. It's important to know, and practically not very relevant, but from a mathematical perspective, it's an interesting idea. So we all know Euclidean space. I'm assuming that you know Euclidean space, right? And Euclidean space, here we have X, which is some n-dimensional vector. We have a norm associated with this vector, which is the square root of X transpose X, right? And we have a notion of angle in this space. So we say that if X transpose Y is equal to 0, we say that X is orthogonal to Y. We have a notion of angle in this space which says that if their inner product is equal to 0, you have those 2 points are going to be orthogonal. Okay, and then we also have a notion of an orthogonal projection. So how do I want to do that? So let's say I have two vectors. Here's this vector X, here's a vector Y. Then I can talk about an orthogonal projection of Y on X. And how do we get this orthogonal projection over there? So we look at Y, and Y transpose X over the norm of X. This is going to be projection in the direction of X, right? And if I look at Y minus Y transpose X over the norm of X, what vector is this? So this, so I take the component of Y in the direction of X and hit a vector X with that. Here is Y, the previous vector. So what is this vector now when I've subtracted out the projection? It's the orthogonal vector, right? This one. And you can very easily check, because if I take the inner product of this with respect to X, I'll get X transpose Y minus X transpose X multiplied by Y transpose X divided by the norm of X. So clearly I made some mistake here. Make this norm of X. So norm of X squared. So X transpose X and norm of X squared cancels. Y transpose X, X transpose Y cancels. You end up getting 0. So you end up getting that this vector is normal to whatever is left over. Okay. Now, if I give you a collection of vectors, so instead of talking about one vector, if I give you two vectors, so that's my here's my plane, and I've got vector x here, x1 here, and a vector x2 here, and a general y, I can talk about a projection onto the plane. So you basically look at a projection that comes onto the plane, and this is 90 degrees that. All of these things you can do in Euclidean space. All right. Now what I want to do is generalize this idea to a general space. Okay, don't forget about this, forget about these vectors and the inner product of vectors. I generally want to just take this idea and transform it to any general space, and the thing that is crucial to extending it to a general space is the notion of a inner product. As long as I have this inner product, I can define a norm by taking the square root of the inner product with itself. I can define orthogonality by saying the inner product is 0. I can talk about projections because the only thing mattered was the inner product and the norm. Both can be defined in terms of inner product. So every time I have an inner product, I can define projections. And when I can define projections, I can do all kinds of things with it. Okay, good. Now, remember, in our story so far, what happened? In SVM story, we started with the notion of doing linear projections, and the inner product that we were working with, or the kernel that we were working with, was this guy. And now we want to move away from that kernel and say I want to use some other kernel, and I want to understand what happens in that kernel. So far we just said, okay, that's a kernel, I will use that kernel and I will do all kinds of things. Now I want to sort of think about the fact that this kernel was supposed to be a generalization of an inner product. Now, is there another space that I could be operating in? Is there a notion that this inner product is just operating as if it was Euclidean space, but in a different space, in a more curved space? Is there something I can do with that? So there was a notion, I will not get into the details. There are some more detailed notions that are needed, but here, for now, we'll just say that a space is a Hilbert space if it has a vector space V, meaning a bunch of vectors, and an inner product x, y, and a norm in this space, which is, let's call this H, to be just square root of the inner product with itself. Now, I'm taking you out on a limb here, just bear with me. It'll turn out that there are some very interesting things we can do if we start understanding them in terms of these spaces. I don't expect you to fully understand what is going on, but at least it will give you a flavor of what is the background story. All right? So I want to define a new inner product, and using this inner product, I want to make everything look like it was a Euclidean space. All right? Okay. So that's just a general Hilbert space. It's a bunch of vectors, it has an inner product, and it has a norm that is defined in this manner. Take the inner product of the vector with itself, take the square root. Now I want to define as something else, which is a Hilbert space, an inner product space, which represents the kernel. So I pick a kernel, this could be the radial basis kernel, I pick that kernel and I want to attach to it a Hilbert space where this kernel has some nice behavior. Okay? So in order for that to happen, what I want is, if I look at all functions of this form, I have been given a kernel K, x, y, so given two vectors, I can compute what that kernel is. If I fix one of them, then this is just a function of the vector space. I fixed one of the entries, and I'm thinking of this as just a function of the other entry. So I want to make sure that this function belongs to my Hilbert space for every value of x. All things that I could generate using kernels should belong to this space. Now there is another peculiarity, is that if I take any function that belongs to this kernel and take the inner product with this function, what it does is that it picks out f of x. So this is, if it has these two properties, we call this Hilbert space a reproducing kernel Hilbert space. RKHS. In fact, there is a one-to-one correspondence between kernels and RKHSs. If you give me a kernel, I can construct for you this Hilbert space where this will work. So given any function, given the kernel, this function induced by the kernel, if I take the inner product, I will get the function f. Now, just bear with me why this is important. And we will do some tricks in a moment. So now, what I want to do is solve this learning problem. So I have a loss function that depends on the target. Let's say it's a classification problem, so it depends on the target plus 1 minus 1, some function of xi, which is the function that we are looking at, and plus some, it could have been some parameter lambda times the norm of this function. What I want you to think about in parallel, which is right, I will write it on this side, was what we were doing for just support vector machines. And so this is simply a generalization of that idea. So we had, for support vector machines, we had minimize 1 over, let's put a summation, I going from 1 through n, of a loss function that depends on Ti and a function W transpose xi plus b plus lambda over 2 norm of W squared. This is what we were doing before. This is a particular kind of function that we were considering, which is the f of xi. And instead, and because this function is completely determined by the vector W, we are saying that W, we are penalizing the norm of W. And we are doing the same thing over here, where we are choosing any function f that belongs to this Hilbert space. Earlier my Hilbert space was just a vector W. Now we have a Hilbert space which is bigger. I want to choose a function in that Hilbert space such that the summation of the losses plus some function of the norm of f is going to be minimized. Now here's the peculiarity of this problem. This is an infinite dimensional problem. Why? Because we are choosing functions. We are not choosing vectors anymore, we are choosing functions. These functions live in this Hilbert space. Keep in your mind a radial basis function. So then this function kx is basically Gaussian vectors with the mean x. They are essentially Gaussian vectors with mean x and standard deviation 1 over square root of gamma. So this is a function, you're taking combinations, all possible combinations of those functions. So here you're allowed to choose any such combination, and you want to minimize this problem. So now you're choosing functions, not vectors, and we want to be able to run that problem. So if we do this, we want to be able to somehow attack this problem. I'll tell you at the end of the day why this is interesting. Just bear with me for a moment. In about a slide we'll be done. So we take the span of all the functions that are supported at the data points. What is a span? If I give you, just to put you into Euclidean space, if I say that I want to consider the span of vectors x1 up through xn, how do you define the span of a bunch of vectors? Just to remind you of your linear algebra.
Basically the vectors on basis of which we can define any other vector as a linear combination.
Perfect. So this span basically consists of all vectors of the form, I don't know, some alpha I xi, I going from 1 through n, and each of the alpha i's is a real number. A linear combination. Okay. So here the span is exactly the same. I'm allowing for linear combination of functions now, not vectors. I'm allowing for linear combination of functions because this dot k dot xi is now a function. So I'm allowing for you to take any linear combination of those functions and call that the span. Okay. Now, because you take any function f that belongs to the Hilbert space, I can break up this function into two pieces. A component which belongs to the span, which is projected onto the span of vectors onto this linear combination, and something which is orthogonal to it. All right? So I take these kernel functions that are supported at my data points, I create its span, take any function that I like which is allowed for me as a classifier. I can take a component of it that belongs to this span and another component that is orthogonal to this span. So now let's figure out what's happening. I'm trying to choose this function f for my classifier. I'm looking at the value f of xi. Because this is a Hilbert space, I know that f of xi can be written as the inner product of f and k dot xi. F and k dot xi. F, I split it up into two parts, f which is projected onto the span plus f that is orthogonal to the span. Inner product is distributive, so I can write this as fs times kxi and fs perpendicular times kxi. But fs perpendicular is orthogonal to kxi. Just by definition, it's orthogonal. So the inner product between fs perpendicular and kxi will become 0. So that disappears. So now you end up getting that this thing is nothing but fs kxi. I use this result again and say that this is fsxi. Just keep with me for a moment, you'll see where we are going. So if you look at the summation of all the losses, you end up getting that this is equal to LT. Instead of f, I can put fsxi because fxi is equal to fsxi. At each of the data points, this function value is exactly equal to the function value at the span. Okay? Now, because this is a Hilbert space, it just acts like a Euclidean space. So if I look at the norm of f squared, it's equal to the norm of fs squared and the norm of fs perpendicular square. Whatever I do with the perpendicular is not going to affect my loss function at all. The loss function is only composed of this guy. The loss function doesn't depend on the perpendicular, so set that equal to 0. It's optimal to set that equal to 0. It's not going to affect your values in any way. Okay? That means if I look at the optimal solution of this problem, let's go back here. When I'm looking at the optimal solution of this problem, the optimal solution of this problem would look like fsxi, which is some projection onto that span. And if that is the case, then the optimal solution would look like this. Take all the data points xj, take a linear combination of them, therefore the optimal solution would always look like that. And this is something called a representative theorem, which says that I took an infinite dimensional problem and reduce it to a finite dimensional problem. Why is this finite? Because all I need to pick are these alphas, which are just n components. So it's a vector that I'm choosing again, not a function anymore. And so effectively what has happened is that by constructing this Hilbert space, I'm able to recover everything that was going on in the finite dimensional space in this infinite dimensional space. And that ends up becoming very useful. So for any f of this form, f of xi can be written as ki alpha, where ki is the ith row of the Gram matrix. Norm of f squared, which can be written as alpha transpose k alpha, which is k is the Gram matrix. And as a result, the optimization problem looks like that, which is again a finite dimensional problem, and you can solve this using any finite dimensional techniques. Now, why is this? From a practical point of view, this makes absolutely no difference. Yes, so it happened. It turned out that there are these Hilbert spaces that you end up getting. The places where this ends up becoming very useful is when, if you want to prove different kinds of properties of support vector machines, or more generally kernel-based methods, now you have the access of a Hilbert space that goes with that kernel. So many of the results in Hilbert spaces can be used to prove various things here, and it becomes useful. For the purposes of this course and this class, I want you to keep in mind this idea that you give me a kernel, I can construct for you a space where everything looks as if it was simply inner product, simply the inner product of two vectors. And conveniently everything works out. The other story that I want to tell you is how are these problems nowadays solved in practice? This is also not there in the notes, but this is something that's again important and interesting. It connects to some other stories. So let's say that I want to solve that problem now, which is some vector problem, lambda alpha transpose k alpha, and then the other side we have the summation of 1 minus ti ki alpha, which is ki is a given matrix, plus b positive part, plus that. Now I want to write this slightly differently, and then we will try to see whether we can make connections to other kinds of things. So the problem that I want to solve, I'm going to write it a little bit different. Let's call this minimize over w and b, or what do they call it over there? Alpha and b. Alpha and b, 1 over n, summation I going from 1 through n of 1 minus ti w transpose not w transpose ki alpha plus b positive part plus lambda over 2, no, just lambda alpha transpose k alpha. So suppose I want to solve this problem. This is an unconstrained problem. What kind of an idea does it come to your mind as to what would you do to solve this problem? Suppose I just say you want to minimize a function alpha over alpha of f alpha. How would you solve this problem? What's a good step to think about it? So is that? Take the gradient. There is a gradient descent method one could use. Okay, so you could say that alpha k, the next iterate, is going to be equal to the current iterate plus I'm minimizing, so minus eta times the gradient at the current iterate. Right? So if you look at that one, we can do the same idea. We can try to do the same idea. This guy is differentiable. What about this guy? This guy would look like a function which does the following. It's 0 for negative and 45 degree for positive. That guy is not differentiable, because at this point the difference is not, I mean the derivative is not available. So we have to fix that somehow. But suppose for the moment that it was fixable. Then I could try to use a gradient descent, but my n is very large. This n is very large. So what can I do in that case? Maybe some of you have seen this trick before. If you have very large number of data points, how do you get around that problem? No, I want to do gradient descent. PCA will not tell me anything about optimization.
Solve batches.
Solve batches, what is the name for that technique? Stochastic gradient descent. So you assume that this is actually, this thing I interpret it as the expectation of some function. So basically it takes value I equals 1 through n with probability 1 over n. That's why I put the 1 over n at the end. So it looks like this is an expectation. So one way to take the gradient, so you can do something called stochastic gradient descent. And the stochastic gradient descent story, what you do is pick I at random from 1 through n. And you take the next iterate alpha k plus 1 to be equal to alpha k minus eta, and now you just take the gradient of this part. Let's say I'm going to abuse notation and say that this is a gradient of 1 minus ti ki alpha plus b positive part. Just one data point. Take a step, next time go back, pick the I at random, keep on going. Question? Okay. Now, in order for this to work, I have to define this gradient. And that gradient turns out to be a little bit of a interesting object. So I want to tell you a little bit, and I'll connect you to other stories that you might be interested in seeing. So the next step, what I want to do is I want to take a function like this, and I want to show you how to smooth it. And these are all things that, if you're interested in this area, I can put some names up for you, and you can take a look of what people have been doing. So this is not, we're going into territories where I won't be able to show you results, but I'll just move you into directions where perhaps things are going to be useful for you. So let's look at this function x plus, which is the max of 0 and x. And yesterday we said that this is the max of 0 less than u less than 1 of ux. So if x is positive, you will end up getting u to be 1. If x is negative, you will take u to be equal to 0. In each case, you will get the maximum of 0 and x. So this is the exact same formulation for that. Now what you do is, if you want to smooth this object, you define a new approximation. Let's call this a function f of x. Now you define something called mu of x, which is defined to be the maximum of the same thing, fu between left 1, u of x minus, say, mu over 2 times u squared. So you penalize it a little bit. This trick is called smoothing. So if you go searching for something, you should look for first order smoothing. And you will get a trick like this. So if you have something like that, now I can define f mu of x. If I want to define this quantity, what do? I take the derivative of that inside. I'll get u minus, or not u. So if I take the derivative of this object, I'll get x minus mu u. And that tells me that the optimum u star will turn out to be the minimum. Well, it's a little bit complicated. Take my word for it that this is the right answer. It'll turn out, u star will turn out to be the minimum of absolute value of x over mu and 1, the whole thing multiplied by the sine. No, that's fine. We can, yeah. It'll turn out to be just x over mu and 1. So that's that. And then, well, okay. U star turns out to be the maximum of 0 and the minimum of x over mu and 1. Complicated formula, but the only thing that I want you to remember is that I can smooth this, and once that happens, that the gradient of this function is well defined. So the gradient of this function f mu of x is nothing but u. It's nothing but this optimum u that you're going to get, u star. So I took a function which was not smooth, I converted it into a function that is almost smooth but with a small correction. And once I have that, I can define what its derivative is. Once I have that derivative, I can put it into the stochastic gradient descent and go from there. No, it's always continuous. We are trying to make it differentiable. Yes, because it's always continuous. This function is continuous. There is no discontinuity. What we are trying to do is make it, when you say smoothing, I'm making it differentiable. Because this is what I need in order to run my gradient descent algorithm. So once I have my function that is differentiable, I can go back here and start doing stochastic gradient descent. So nowadays, if you are doing not the scikit-learn variety, but if you're doing really very large scale SVMs, people go down this route. They're no longer solving the dual, they're going back to the primal. That problem can be constructed. The derivative of this part is pretty easy. It's just 2k alpha. And then you smooth that part, and then you do stochastic gradient descent. And this ends up becoming the more faster way of doing things. And in any case, what stochastic gradient descent tries to take advantage of it is the fact that if you have lots of data points, if you have lots of data points, you're not trying to get the vector W very exactly because there's already noise. And one more comment from the RKHS formulation, this formulation here. Down here, I have to use a norm that corresponds to the Hilbert space. And so these norms, L1 norm or Lasso style norms, which do not correspond to Hilbert spaces, but they correspond to Banach spaces, they cannot be used in this setting. So you can't use L1 type or sparsity inducing norms, but you can use this RKHS. Now, of the more theoretical ideas that we just talked about, the two things I want you to remember is this notion that behind every kernel there is actually a Hilbert space that you want to be able to work on. And the second thing is that for very, very large scale SVMs, now what you do is do not go to the dual. You take this function, interpret this part as if it's an expectation over the various data points, smooth the hinge loss function, and then use stochastic gradient descent. That turns out to be the more effective way of doing things than what comes from one of these packages. Okay. They're popular for both classification and regression. This I'm just summarizing some ideas, and then I'll show you two more things that might be of relevance to some people. They do have some weaknesses. They can only be used in ad hoc way for multi-class classification. Outputs of an SVM classifier a decision rather than a probability. This sometimes becomes a problem because it's a hard classifier. It's just telling you it's either this class or that class. Remember in EM, we did not like hard classifiers. We liked soft classifiers, which give me a probability distribution of what's going to happen. So Bishop has proposed a new method called relevance vector machines, and I'll show you a little picture of it as we go along. As an alternative to sparse kernel technique for regression and classification, this is a Bayesian method which produces posterior class probabilities, can handle multi-class classification. It's much slower to train than SVMs, but then you don't need cross-validation anymore. You end up getting rid of cross-validation. Evaluation of test points are much faster than SVMs due to generally better sparsity. It has greater sparsity to do better. So I'm just going to show you what the idea is. And this was motivated really because somebody asked a question. So I'm just going to show you. I won't go into detail, but I'll just tell you what the general picture looks like. Let's see. So these are some lecture notes that are reasonable. I will send it to Raghu, and he can share it with you guys. So remember, this is support vector machines, a well-known supervised learning method for classification or regression. We are given n training points with some labels +1, -1. Using the pairs x and yn, an SVM can be trained, and given a test vector, the SVM's output can be written as this. It's some weighted combination of a kernel plus some offset. So wi k x xt is the test point, xi are the points that I have, times the test function. So this is approximately the function that we want to generate. And what we have done is we created either an optimization problem like that one or a quadratic program to try to compute these weight vectors W. What this relevance vector machine idea was, let's say we have data points. We construct the target yn for the data point, for the nth data point. I'm going to assume that it is of the form fxnw plus epsilon n. What is this function? This function is exactly that function. This function up here. So I pick a weight vector w, that defines for me a function. Here I'm saying that yn is going to be xnw plus epsilon n. So if epsilon n is assumed to be Gaussian with mean sigma squared, then the probability for yn given xn is normally distributed with mean fxnw and standard deviation sigma or variance sigma n squared. So now what we are doing is that instead of saying that yn is actually a value, a regression value, we are saying now it's a distribution. And Therefore, the probability distribution for all y's can also now be written in terms of the weight vector W and sigma squared, which is the noise that I've assumed. To avoid overfitting, this relevance vector machines defines a zero mean Gaussian prior distribution over W. It assumes that the weight vector W itself is sparse. It's drawn according to a normal distribution with mean 0 and variance 1 over alpha I, where alpha is a hyperparameter associated with weight W and A is simply the diagonals. Given the distribution, you end up getting, what you want to do now is you set up a Bayesian problem. So now we have a forward problem. The model says that the W is chosen according to this distribution, Y is given by that distribution, but now the data is given to me, and so from that data I can compute the posterior distribution. The posterior distribution of the weight W given Y and X and alpha and sigma squared. So I can go back, and this is what the mean vector looks like, this is what the standard deviation looks like, the optimum value for alpha and sigma squared. What are alpha and sigma squared? Alpha are what determines this variances of this guy, and sigma squared is the error that is associated over here. You can optimize that, and I know I'm going pretty fast, so I don't want you to really I'm not expecting you to know what is going on over here. All I'm trying to say is that the whole idea of support vector regression, for example, can be embedded into a Bayesian setup, and here we are trying to find the posterior value of W. When you do all of these calculations, you can compute it, and you end up getting some values for, basically you have an EM like calculation that you end up doing here to be able to compute what happens to the alphas. And if you do that during the optimization, many hyperparameters alpha I tend to infinity, and the corresponding weights Wi become 0. The vectors xi corresponding to the non-zero weights are considered as relevance vectors. The same story as support vectors, but they are now called relevance vectors. And it turns out that in practice you have a lot fewer relevance vectors than support vectors. You can do the same thing for, where did it go? You can do the same thing for classification. Now what you're saying is that if I want to classify a weight probability distribution of Y is a sigmoid function. Sigmoid function is of the form sigma of x is of the form e to the x over log of something, I forget what it is. Log of e to the x over 1 plus e to the x. A function of this form. And so here what you're saying is that it's a sigmoid function on that linear function. This is 1 minus the sigmoid function on the linear function. This is to the power yi, whether yi is 0 or 1, and this is to the power 1 minus yi. Once you have this forward distribution on y, you have again a prior distribution on W given alpha. You can compute the posterior distribution on W again, and as a result now you can do the same trick, and once you get the posterior distribution you end up having a whole distribution of the classes. So the relevance vector machines, what they are trying to do is take the support vector machine idea and transform it to a point where you want to have a distribution of classes on classes rather than having a number, rather than saying that this is class 1 or class 0, and they tend to perform much better in practice than support vector machines. Relatively newer technique, this was invented by Bishop, there should be a reference here, in 2006. That's tipping in 2001 started it, 2006 was when it started to stabilize. So it's a relatively newer idea, but it's picking up steam quite a bit. So that's, and the last piece that I want to talk about is another idea that people have been using, which actually happens to work very well with music, is, let me see if I remember this paper well. Is it Lancreate or Lacreate? So this is a nice paper. This was a question being asked before in the module in the morning, where how do we know what kernel to use? What these guys do is they basically find the best combination of kernels. They take all kinds of kernels and then compute what is the best combination of kernel that will work for the data that they have.
That is like assemble
Yes, but they don't do it ensemble. So they are not doing an ensemble, they're not doing it probabilistically, they're actually doing it deterministically. So they are like an SVM. So this is sort of trying something that you can embed into an SVM to try to find the best possible kernel. So the advantage of deterministic methods is they tend to be faster than these ensemble methods. So they can take advantage of ensemble methods to be able to do things. So that's an interesting idea that has been around for some time. It's worked very well with music. Lankiert, who is the first author, he's now in, I think, UCSD, and he's been working with a classification of music. He was very involved with this app called Shazam for a while, where you make it hear some music for a bit and then tells you what the song is. So it's basically they've been using techniques like this to learn the songs. All right, so that brings us to the end of SVM, and now depending upon how much, we'll come to the last topic, or maybe if I have time tomorrow, I will do more, which is doing dimension reduction. And I don't want it from here, I want it from there. Where did it go? Dimension reduction. So the next piece of techniques are basically trying to understand how I can take an information in a very high level. Here's what the story is. I have a bunch of data points. D is the dimension of each of these data points. So it's a matrix x1 through xn. I have n samples of a d-dimensional random variable. Think of D being really huge in these cases. So each column, for example, is a 2D image that has been converted into a column. So think about a 1024 by 1024 image that I have put it into a column. So D is a million. Is it a million? No. Yeah, 10 to the power 6. So D is a million, and n is the number of different images that I have. So that's what this matrix capital X looks like. It's a collection of these vectors. It could be gene responses where each column is a measurement at a particular time. So D is the number of genes that I'm interested in, and each n is going to be observations of these genes at different points. So these will be 0, 1 vectors, for example. It could be prices where each column is a price at a given time. And the whole story here is that we want to find L variables, combinations of the D variables, in such a way that it contains most of the information of X. And that's what this principal component story is going to be. I want to combine different dimensions of X. I have D of them. I want to get fewer number of components that preserves the information. We will start with principal components, and then we will argue that principal components might be one idea, but maybe there are other things one could do. Then remember, it's gone from the board. Principal components are also associated with a Euclidean space. There is a notion of orthogonality. The SVDs are taken with respect to some vectors, and there is a notion of orthogonality, right? We also saw in support vector machines that maybe the right notion of orthogonality is not the obvious one that we see. Maybe the right notion of orthogonality is through a kernel. A kernel defines a different inner product. We saw towards the very end that we can construct a Hilbert space where this kernel is the right inner product to be working with, and that gives me an idea of how to do things. So maybe there is a way of taking kernels and defining kernel principal components. This notion that when you take inner products and you make the inner products through a kernel, that might give us a different way of looking at principal components, and we'll do that as well. So let me just go back a slide so I can tell you where we are going. There is kernel PCA. Is principal component analysis. We'll look at some applications of principal component analysis. There's some idea called latent semantic analysis, which is PCAs applied to documents, which are starting to become an important topic. And then we will sort of say, look, PCA is just one way of factorizing a matrix. Maybe there are other ways of factorizing it, but this is an error here. It's a dictionary learning. There's an extra S, remove that. We are looking at non-negative matrix factorization. That turns out to be very interesting as well. Then we'll look at matrix completion, which is sort of a variant of the problem where some of the data points are missing and I want to figure out what to do with them. And finally, we will see that some related ideas are connected to reputation systems and PageRank. And that's where we'll finish this topic. Okay, going back here. So, suppose there exist principal components B1 through Bn, which is in RL times n. For each of these data points, I can compress the information from D dimension to L dimension. So each of these vectors B1 through Bn are L dimensional vectors. Factor loadings A1 through AL, such that A transpose A is equal to identity, meaning each of these factor loadings are orthogonal, orthonormal. They are orthogonal to each other and the norm of each of these vectors is equal to 1. And if we have components of this sort and x is equal to A times B, then we can say that these principal components are nothing but A transpose x. So you take each of these factor loadings, hit it to the vectors, that tells you what the corresponding principal components are going to be. So we want to be able to find a factorization of the matrix X into A times B. Okay? And this is why on this slide I am saying that factorization is the right thing to think. Don't think of this as principal component as something which is sort of the best thing out there. We want to think of it as simply a way that it factorizes things. Okay? This particular factorization, which is called principal component analysis, has some nice properties which we will talk about first. And then we will argue that maybe that's not the best thing if I'm after something else. PCA may not be the right thing to do. So we'll take a detour and come back to this PCA story with defining something else. Suppose I want to construct a rank R approximation to this matrix. So I have a matrix x1 through xn. This is matrix X where the columns are there. And I want to construct an approximation to this matrix which has lower rank. What is for this matrix, what is the maximum rank that it can have? What's that? Minimum of D or N, right? So minimum of D and N. So this R better be much smaller than D and N. So the idea is that you want to create an approximation which is smaller than that. And why do we hope that might happen? Because it's possible that the different components of X have redundant information and therefore there might be some overlap there. I can reduce the rank. The number of the information in different columns might also be redundant and therefore I would be able to get something better. In reality, it will always be an approximation. It will never be, the rank of X is never going to be very small. It's going to be small if you're willing to ignore some errors. Okay? So that's the optimization problem that I want to solve. I want to minimize the difference between X and a matrix A such that the rank of A is less than or equal to R. This is the low rank approximation problem, right? I have this matrix X. I want to approximate it by another matrix A which has small rank. Now suppose this A is allowed to have two different norms. One is the Frobenius norm, which is basically take all the components of the A matrix, square them up and take the square root. There's something else which is called the spectral norm, which is the maximum of the vectors that you can generate by hitting the matrix A to a vector V whose norm is equal to 1. So you can think of this matrix A as an operator. It takes vectors of dimension n and returns for us vectors of dimension d.
The rank of A can be even less than R.
Yes, I allow for the possibility. It doesn't. I'm not restricting it to be exactly R. Let's allow it the possibility of being less than or equal to R.
Had it been greater than or equal to R, it cannot be.
That's stupid, right? Because I'll take X.
Yes.
So then, if you allow for rank to be large,
That means it can reduce even beyond R.
perhaps. Okay. Here's an alternative formulation. This matrix formulation can also be written in this form. Minimize for a matrix A in R D times R and B in R times N such that X is equal to AB. Now we are starting to see that this starting to look like a PCA type problem. This rank minimization problem, or finding the low rank approximation, is PCA type problem. The n columns of X can be well approximated by the R columns of A. As a result, we have a low rank approximation for X. So how do we connect these two ideas? We connect these ideas by a singular value decomposition. So for any matrix X, which is a D by N matrix, you can always write it as this combination, U D V transpose. And if you expand this out, you have this formulation of I going from 1 through R, where R is the rank of this matrix X, some non-negative number sigma I, Ui Vi transpose, where each of the Ui's are an orthogonal basis for the D-dimensional space, and Vi's are the orthogonal basis for the n-dimensional space. You can choose a basis for the d-dimensional space, and you can choose a basis for the n-dimensional space, such that the action of this operator is simply diagonal. It's just sigmas along the diagonal. So D is a D by N non-negative matrix where Dij is equal to 0 for I not equal to j, and Dii is equal to sigma I. The diagonal elements are called the singular values, and we assume that the singular values are ordered such that sigma 1 is greater than sigma 2 is greater than sigma r, which is greater than equal to 0. You can always choose that the singular values are always greater than equal to 0, where r is the minimum of D and n. Some of these could actually be equal to 0 even before, so that allow for the possibility of that happening. Okay. Here is just a construction. First, what you take into consideration is the fact that if you take the matrix X transpose X, that becomes an n by n symmetric matrix. Because it's an n by n symmetric matrix, I can compute its eigenvalue eigenvector decomposition. So these are basically the eigenvalue eigenvector decomposition. For the Ui, simply set it equal to x times Vi. Vi is the eigenvector divided by the norm of xi, and set the sigma I, which is not there, sigma I, set that equal to the norm of xvi. And that gives you the construction of what is happening. Each of the Vi's are going to be orthonormal because they are eigenvectors, and you can show that the Ui's are also orthonormal. And sigma I's become the diagonal elements. Okay, all this is great, but what does it help me? So first thing, singular values are by themselves very interesting objects. If you look at the Frobenius norm of a matrix, and remember the Frobenius norm was defined as take all the components of that matrix, square them, add them, and take the square root. That Frobenius norm is nothing but the L2 norm of the singular values. So there is a connection for basically for every norm that you define for the matrix, there is a connection to defining a norm for the singular values. So it turns out that singular values in many cases almost represent the matrix. The spectral norm is the L infinity norm for the singular values, the maximum value of the sigmas. The nuclear norm, which is the L1 norm of the sigmas. Schatten norm, these are more generic norms, which is basically, it's not L infinity here, sorry, this is LP norm of sigma. So sigma I to the power p summed and to the power 1 over p. And therefore this becomes a L infinity norm of sigma. So it turns out that all of these different objects have a very nice connection to singular value. If you compute the singular value, you can compute all kinds of things. And this has become, the singular values have become the core of how you do matrix decomposition, and in fact have remained the core of a lot of linear algebra around matrices. So these norms play an important role in matrix completion and decomposition problems. Now, define a rank KSVD to be simply take the first k largest singular values, construct this matrix xk. I take the SVD of the matrix X. I assume that the singular values are in decreasing value. So if I take the first k of them, this definitely gives me a rank k approximation because there are only k vectors involved there. And one of the nice results, this is the Eckert-Young-Mirsky theorem, which says that let A be any rank k matrix that you can pick. You look the difference of x minus a norm 2. This is the operator norm or a spectral norm. That is going to be greater than equal to x minus xk operator norm, and that is exactly equal to sigma k. If you look at the difference between x and a in terms of the Frobenius norm that is going to be greater than x minus xk in terms of Frobenius norm, which is defined as that, k plus 1 to r sigma I square. So the SVD provides the optimal solution to the low rank approximation problem, provided you are measuring distances by either the spectral norm or the Frobenius norm. If you decide to measure differences with respect to some other norm, then SVD is not the solution. SVD is the solution of the rank approximation problem only for these two norms. There can be other solutions. Remember, this one simply says that you pick any one, it cannot be better than SVD, but there might be other solutions that are equally as good as SVD that might have other desirable properties. So when we look at other kinds of approximations, we want to look at the possibility that non-SVD solutions might give me something better. And there have been other proposals that have been made. For example, let's go back over here. One thing that has become very popular, we'll come to it towards the end, is that you want principal components and you want factor loadings that are non-negative. I want to take a product of matrices X is equal to AB, where both A is non-negative and B is non-negative. Why would that matter? Because X might have, for example, one way of thinking about it is, let's say X is some kind of a joint probability distribution. I want to divide it into two parts, a probability distribution A and a probability distribution B, because that gives me some nice interpretation. But I'm not allowed to make negative numbers there. Or X happens to be an image. If X happens to be an image that is non-negative values, trying to do a PCA on the image turns out to be a little bit bizarre object, because the factor loadings, if we want to interpret these factor loading as somehow the base images, but if it has negative values, I can't think of it as base images. I can do machine learning with it, I can do prediction with it, I can do classification with it, but if I want to somehow come up with this idea that these are some base images that are interesting, then I won't be able to do that. So PCA is not always the answer, because there are some other desirable properties that one may want to impose. Where did we go? Here. Sometimes what we do is that often the number of data points n is less than d, so instead of going to compute the entire SVD, you do something which is called an economic SVD. The economical SVD, which just picks up very small number of singular values that ends up giving me information. Also, often this data has noise, and so one way of trying to make things faster, which is getting around this computing the eigen decomposition of various matrices, you can use randomized projections, that's not projects, but use randomized projections to compute a basis for the range space of X, and once you have that, you can do faster things. We won't get into the details here. This has to do with the fact that for very large data sets, trying to compute the SVD itself becomes a very hard object, and there are techniques that have been available now to make it faster. What we want to do is show a little bit of the various kinds of applications that people have been using. For PCA, they have been used in data compression. They've been used for reduced rank LDA, which is linear discriminant analysis. They've been used for nearest neighbor classification, financial modeling, latent semantic analysis. When we go to this missing data part, we'll use other ideas and we'll not use PCA as much there, but we'll come to it towards the very end of this module. So I want to just spend some time giving you some ideas of how various things are used. So here, this is what HTF stands for. Let me go back, it should be on the first slide. Where did it go? Yes. So some material has been taken from the Bayesian reasoning and machine learning. There's also HTF is Hastie, Tibshirani, Friedman. So they have a nice book, and some of the pictures that I've taken are from that book, and so that's what the HTF stands for. So it's figure 14.22 from HTF. They have displayed 130 handwritten threes from a total of 658. They are digitized as 16 by 16 grayscale images, so you can view them as points in R to the 256. And that's what this is what it looks like. So each of these is a particular example of a 3, and we want to see if the information in all of these threes can be summarized as something smaller. All right? So each of these can be viewed as a vector now. So you take the 16 by 16 image and collate it as one vector, which is r to the 256. And what we want to understand is what can we do some kind of PCA to learn what the variations are. So first compute the mean, and then you compute the SVD of the residual matrix. So x bar is just the mean of all the n vectors that you have. Then you compute the SVD of the residual matrix, and then what they do is they just keep the first two singular values. So x bar is the mean, v1 happens to be the first singular vector, v2 happens to be the second singular vector, lambda 1 is the first singular value, lambda 2 is the second singular value. And you represent each of the vectors as a combination of these two singular vectors. So that's the base mean. This is what is happening along the first one, this is what is happening around the second one. The first component accounts for the lengthening of the lower tail, so it's sort of increasing the tail, upper tail and lower tail. The second component accounts for the character thickness. And you end up, they plot the first two principal components along with images that are closest to the vertices of the grid at 5%, 25%, 50%, 75% and 95% quantile. So what they have done is that they have done these two PCAs on the two dimensions. Out here is the 50th percentile, which means that it's the median. And these dots that have been put are been taken from over there. So if you take one of these, it's out here, the lower axis is becoming thicker. And if you go up there, go down here in this direction, then the entire tree becomes fatter. So in this direction, it's thin trees to fat trees. In this direction, this tail is short to tail is long. And that's what is characterizing what is happening to these vectors. Everything else turns out to be lower levels. So we don't end up, so the left panel, which is the panel that I didn't show you, is the first two principal components of the handwritten threes. The circled points are the closest projected images to the vertices of the grid defined by marginal quantiles. The right panel is the images corresponding to the circled points. These show the nature of the first two components. So this one thin to fat, that one short bottom to long bottom. And that represents so in some ways the variations that are available in this big panel have been captured really by just the variations in this small panel. That's the information that is available. After that there is still information, but it's lower randomness compared to what the first two are capturing. This is a picture that is taken from Barber using 100 training images. Each image consists of 92 by 112, 10,304 grayscale pixels. The training data is scaled to represent an image. The components of each image is equal to 1. The average value of the pixels across the images are about 9.7 to 10 to the power minus 5. This is a subset of 400 images in the full Olivetti Research Face database. And so if you do PCA on that, the eigen images found using SVD on the images in 15.5 and taking the mean and 48 eigenvectors corresponding to the largest eigenvalues. So these are basically 1, 2, 3, 4, 5, 6, 7. 7 times 1, 2, 3, 4, 5, 6, 7, 49. So this one is the mean. So take 48 eigenvectors. Remember, for all of these things, what you first have to do is first you have to remove the mean and then do the SVD on the residual one. You want to do the SVD of the noise, not the mean. So the mean is taken out and everything else you do the SVD in the residual matrix. So same thing over here, you first take out the mean, and the mean looks like in this particular case has no real features except that it's not black, it's got some level. So that's the mean, and then you have 48 eigenvectors with the largest eigenvalues. The images corresponding to the largest eigenvalues are in the first row, then the next 7 in the next row, and so on. The root mean square of the construction is 10 to the power minus 5. a small improvement over PLSA. We will get to this method in a little bit. Now the problem with this story is that although I'm showing you these images, there is no guarantee that these images have everything non-negative. Because this is eigenvectors. When you do the eigenvectors, some component could be negative. So what do? You just make the negative component 0. So whenever you see a negative component in this image, you set it equal to 0. Now it turns out that there is a technique available, which we will see a little bit later, where you can take these images and actually compute non-negative decomposition of that matrix. And we'll see a very nice connection between that non-negative the constructions that are there for non-negative matrix decomposition and the EM algorithm that we have seen yesterday and today. We can use that EM algorithm to get non-negative matrix factorization. For here, we are just using SVD in eigenvectors. Okay, now I'm going to do a little bit of a detour into classification, and then I'll show you how PCA becomes 215. Let's try to do this and then we'll take a break. One thing to keep in mind is that what the PCA is trying to do is basically saying that I have a lot of information, but maybe a lot of this information is noise and I should not be relying on them. And similarly, when you do any kind of classification, you have data points, you're trying to use these data points to do classification. It's possible that some components of this matrix of data that you have is actually very noisy and maybe should not be used for classification. And PCA gives us a way of doing it. So this is not something that we talked about in these modules, but perhaps you might have seen it elsewhere. It has connections to this mixture of Gaussians that we did in EM, and it works in the following. Suppose there are k different classes. Pi k is the probability the data comes from class k. For class k, the observations are distributed according to a Gaussian distribution with a common covariance matrix. So if the data point comes from class k, then the distribution of the data is given by x minus mu k. The mean is class dependent, but the covariance matrix is class independent. Okay? So if the covariance matrix is class independent, you get a classification methodology which is called linear discriminant analysis. Okay, we'll see what it means. So you've got data xi, yi. There is no missing data here. Yi is a class label, I going from 1 through k. Then you can estimate the parameters for this product by this formulation. Pi hat k is simply this is the indicator function that yi is equal to k, sum it over the data in 1 over n. Mean corresponds, take all the data points for which the class label is equal to k and take its mean. Sigma hat is a little bit different. You take 1 over n minus k, why n minus k? Because I want to make it unbiased. Summation of k going from 1 through k. Take the summation of all data points for which the class label is equal to k, xi minus subtract its class specific mean, xi minus its class specific mean transpose. In this particular case, you pool data from all the classes because you're assuming that the sigma is class independent. Okay? So you can estimate this. Based on that, we can now create a classification function. I am given a new test point x. How do I classify this? I take the maximum over pi hat k fkx. I take the maximum of these two, but taking a maximum of that is equivalent to taking the maximum of the log. So it becomes log pi k plus log f hat kx. If you forget about all the constants, then the log looks like this. It's log pi hat k minus 1/2 x minus mu k sigma hat inverse x minus mu k. What did I end up doing? Okay, that's fine. If you expand this part, you will have a term x transpose sigma hat there's a transpose missing here, sorry, just put a transpose there. X transpose sigma hat inverse x. That term is going to be the same for all values of k, so I can ignore that part. It's not going to make a difference in the maximum. The leftover components are over here. X transpose sigma hat inverse mu k, log pi k, which comes from there, and the last term, which is minus 1/2 mu hat k transpose sigma hat inverse mu k. All those terms are over there. So one way of looking at this transformation is to simply say that it is a maximum of this linear function. How do I classify? I take this linear function of x, find the maximum value of k that maximizes this linear function. That is the classification that I'll be using, right? Background story, because it's basically once you start with Gaussian, you estimate the parameters, and all of this just falls through. Okay. Now, let's remember this sigma guy over here, this matrix. This has been generated from data. And so it's possible that this is very noisy, that it has some very small eigenvalues that I should not believe. I should not believe that those small eigenvalues have information. I should get rid of them. So let sigma hat, which is u d u transpose, be the eigen decomposition of these, where u is orthonormal, D is a diagonal matrix with the positive eigenvalues of sigma hat. Sigma hat is symmetric, so I can get that. So you redefine a new matrix, a new vector x star, which is D to the minus half u transpose x. So now for x star, the covariance is identity. And now the discriminant function can be written very simply as this. It's log pi k minus 1/2 x star minus mu k star squared. Now, when you look at this function, it becomes actually very trivial. What we are trying to do is we want to look at the centroids mu hat k, whenever I find a point x star, I really want to classify it to the closest value of mu hat k, except that I have this complication of log pi k coming from there. The log pi k is something that I have to worry about. So take these centroids. The k centroids lie in a k minus 1 dimensional subspace. So classification reduces to the following idea. You project onto this subspace, classify the projected points to the nearest centroid, adjusting for the log pi k's. Bear with me, I don't want you to pay too much attention. The story that I want to is coming in a moment. So once you do this centroid idea, now what you can do is perhaps the smallest values of sigma hat are just noise, and I want to get rid of them. So what you do is you choose a lower dimensional space that maximizes the between class variance relative to within class variance. And this is the technology that is used. You first change variables, let m star be the m by k matrix of class centroids under these new coordinates. Treat these centroids as observation and compute a new coordinate covariance matrix. Take its eigen decomposition and use the largest eigenvalues of that. So ZL, which is VL transpose x star, is the Lth discriminant variable. So central computational tool for reduced rank LDA is simply PCA applied to these centroid, applied to this matrix. And here's an example of what happens. So a comparison of principal component analysis with Fisher's linear discriminant for linear dimensionality reduction. Here the data is in 2 dimensions belonging to 2 classes, red and blue, is to be projected into a single dimension. PCA chooses the maximum variance shown by the magenta curve, this one. If you did just a PCA on the data itself without worrying about anything, you will pick this direction because that is where the variation is the highest. But that's not what we want, because that is not going to, if you just simply did the PCA on the data points, it's useless. Which leads to strong class overlap, because if I project it on that, you will get a overlap that's going on. Instead, what you should do is first find the center of this point, center of that point, and then do a PCA on the leftover part, whereas Fisher's linear discriminant takes account of the class labels and leads to a projection onto the green line, which gets much better separation. So what you do is do not do the PCA directly on sigma hat. You first do a change of variables, get the centroids, treat the centroid as observation to get a new covariance matrix, and do a PCA on that matrix. That gives you better performance for doing discriminant analysis than doing a PCA directly on the data. The punchline of the story, PCA is the tool that I'm going to be using, but I need to figure out what to do the PCA on. You can't simply just do a PCA on something and hope everything works out. In this particular case, if I did the PCA directly on the data, I would get this line, which is utterly useless. But if I took into consideration that the data actually comes from two different classes and then constructed my PCA, then I get the green line, which is a much better analysis. So when you think about PCAs, don't think about PCA being like, that there is only one way you can do PCA. PCA is basically trying to keep the information in the underlying matrix. But first, you have to construct that matrix correctly. You have to construct a matrix that is most relevant to the PCA analysis. All right. Yes?
When you say before, don't directly use the given data as it is and do the PCA, that is the data that we get, and you remove the centers of it. What is that?
So what you do first is that you first transform these data points. So in this particular case, we are doing two SVDs. So first SVD, you take, okay, so let me try to tell you what is the easiest way to do it. Okay. So what you first do is you change the variable so everything looks spherical in this variable. Everything looks, all the data points look, instead of ellipsoidal, which is, if you look at these data points, they look like ellipsoids. So you first make them spheres. And for that, you use the SVD of the entire thing. Because what you want to do is take all the data points and make them look like they are sitting in spheres. So do the SVD of the entire matrix that you get. And then once you do that, you get a center of this cloud, because this is already a class label. So you get the center of that cloud, which is going to be this point mu star 1. Then you'll get a cloud center of another cloud, which is mu star 2. You have two data points now, right? Now in this particular case, we don't even have to do an SVD, because what you end up getting is that if they look at the difference between mu1 and mu2, that's the only direction that is important. If you had many classes, then you would get mu1, mu2, mu3, mu4. Take that matrix, do an SVD on that, and now figure out what are the right directions to do. So you'll have two SVDs that will happen.
Sir, when you do a principal component analysis in SPSS,
I have no idea how SPSS works.
so there is an option that asks for select your rotation time. What is that?
I have no idea what SPSS is.
Like whenever we go do a
Let's take it offline, because I won't be able to answer your question. So there are many applications of PCA in finance as well. I don't have specific examples for you. Anytime you have any kind of random movement, you want to be able to represent them by lower level models. Term structure of interest rates, it's useful for interpretation, it's useful for building factor models. And the typical way that people use this story in finance is that you take the data, you do the PCA, now you get the principal or the eigenvectors, not the principal components, but the factor loadings. And instead of taking the principal components that came from the actual data, you can stress test each of them differently. You can figure out how to stress each of the different components or the eigenvectors that you end up getting. And that ends up a good way of stress testing the underlying information. You can do it in future strips. Useful, again, it's for hedging and building of various kinds. You can build factor models for equities. You can use it for scenario generation and risk management. You can do it for estimation of risk measures such as VAR and CVAR. All of those things are important, and there are colleagues of mine in my department who sit around designing all kinds of these techniques to try to get better ways of interpreting what is going to happen in markets. Okay, we will stop here.